Hey, welcome back. This is episode 6. This is platforms, mountains, and plateaus. That's the French spelling for plateau with an X at the end there, meaning multiple plateaus. We're going to start it off actually by looking at a map from the USGS here, and that is to show you the global distribution of these things around the world here. The shields are in orange here, the platforms are in pink. And so these are areas around the world that we consider to be really pretty stable and based on the craton. And so the craton would include those two parts right there. Orogenic belts are on the light blue, the kind of the cyan color blue. The light blue is actually basins, not necessarily mountain basins, but these would be basins that may be in a cratonic setting, but not all of them are. And so, but anyway, we're going to look at these areas in more detail. So the platform is a stable ancient part of a continent. The craton, in fact, is that stable part that underlies a platform. And then the areas where all of the rocks, all the sedimentary rocks and the sediments, most of the sediments, in fact, have been scraped off of those sort of areas. So this is the map of the world showing you these things, and they are distributed around the world on the continents, but primarily the continents. So the platform are the areas that are stable, but then covered by these relatively flat-lying sedimentary rocks. Contrast to the shields, however. The shields are where you get that crystalline rock right there at the surface. And then it also contrasts with areas that are mountain belts. And so mountain belts are areas where you get deformation from either collisions or other sorts of geologic processes that would impinge upon areas that may have been platform at one time, but then got twisted, buckled, and deformed in some way. And so deformation includes things like fracturing, faulting, and folding here. And so in the next diagram here, I want to show you what it looks like to be on a platform here. That is a Precambrian granite at the bottom down here. Now this is called I think this is just west of Cody, Wyoming right here. And as you go into the mountains west of Cody, Wyoming, you're heading towards Yellowstone here. And so that is a granite body there. You can see how pink it is and everything. And so that is a granite body on the lower right here along the road. And above that, you can see all of these layered rocks. Well, those layered rocks there, that's kind of a dead giveaway for most sedimentary rocks. Most sedimentary rocks are layered like that. And in fact, that's actually a sandstone right there. That's called the Flathead Sandstone. And so even though this is in a mountain belt here, this is not regarded as being in the platform, but it's like platform rocks and how platform rocks behave. Those are flat-lying rocks above an igneous rock body here. And so the igneous rocks did not intrude into those rocks because it would have baked those rocks at the bottom. In fact, that's one of the ways you can tell whether something is an intrusive or it's just been eroded and then the sediments have been deposited over the top. In this case, the sediments have been deposited over the top. It's not an intrusion. And that surface right there at the base of that sandstone is called a nonconformity. Now, nonconformity is just one variety, one flavor, if you will, of an unconformity. Unconformities just mean there's been a disturbance or a break in the rock, and it happens where you get erosion and deposition of another rock over the top. And so we're going to talk about the 4 kinds of unconformities here in a little bit. But that's the Flathead Sandstone right there, and you can see the flat-lying rocks that go over. I mean, they are dipping a little bit here, but they have beveled, in fact, some of that Precambrian basement rock that's down below them there. So that is the flathead there. Here it is up close from the other side of the road, in fact. And so there's Nancy for scale here. You can see the pink down there that is granite, and then you can see blobs of material that were included into that granite just behind Nancy there. There's that sort of dark gray area in there. That would be another piece of basement right there, and that is material that would have been dating back over 550 million years ago, and this one's probably closer to 1.4 or 1.3 billion years old here. I'm not exactly sure what the absolute age date is on that granite there. But above that, you can see that's surface of erosion there. And on this side, it's actually irregular, but it's still regarded as what we call a nonconformity. A nonconformity is where you have crystalline basement rock that's overlain by sedimentary rock. Now, that's just one variety of unconformity. So there are 4 varieties altogether. So that is the flathead sandstone right there. You can see some of it's got a little bit of dark green shale in it there. Those are those thin bedded areas in there. And then the sandstone itself is actually the thicker bedded, kind of weathering orange sort of beds well above Nancy there. So we get orogenic belts as well, but orogenic belts usually are going to affect the rocks that are in the platform. So platform rocks that have been impinged in some way would tend to get this sort of like deformation in them. And this one's kind of cool right here. So this is actually in northwestern Colorado here. Actually, just going into Utah here actually. So this is the Sheep Creek geologic area, Sheep Creek Canyon geologic area, and that rock right there is a limestone that looks all twisted in there. You can still see that it's layered, but it's also been folded somewhat. Those rocks are what we regard as Mississippian in age. They're roughly about 350 million years old, 340, something like that. And the rocks to the left of this, in fact, are much, much older than that. And so that's another nonconformity when you get just below here. And so that one's actually a structural deformation more so than it is. I think it's in fault contact there rather than being an actual nonconformity. So the fault is actually juxtaposed those two different rock types here, the granite to the left and the limestone to the right. So anyway, it gets us to the point, it's like, well, what do you mean when you can deformed platform rocks and you can turn them into orogenic belts? That's what happens all the time, in fact. And we regard them as separate entities, sort of. And so this would be regarded as an orogenic belt here. So where do they begin and where do they end? Well, it's a little bit of a gray area, right? So if they're deformed, as you can tell here, it's like we're going to regard that as being part of an orogenic belt. So anyway, here are the common rock types that we get with these sedimentary rocks that may or may not overlie igneous rocks or igneous basement. So that is in fact, you're going to get breccia. Breccia is a rock that's made out of bits and pieces of other rock. A conglomerate is also, and the difference between a breccia and a conglomerate is that a conglomerate has rounded clasts and a breccia has angular clasts, and so things that haven't been necessarily transported don't have the sharp edges knocked off by being transported in rivers and streams and things like that. So a breccia and conglomerate are pretty common geologic sort of like products that you get around mountains. But anyway, a conglomerate has the rounded bits. Also, you can get sandstones. If you've already seen the flathead sandstone there, you can get finer grain rocks that are called siltstone there. And then you can get shale. Shale is a rock that's made out of clay minerals, essentially. Being made out of clay, it tends to be very, very susceptible to erosion, and so it can get weathered away. And so very commonly when you see a shale, it's going to have a slope or something like that it forms. You see that a lot in the Grand Canyon. The shale intervals in the Grand Canyon tend to be slopes, whereas the limestones and the sandstones tend to be vertical cliffs. And so, but those are the types of rocks that you get commonly with sedimentary rocks: breccia, conglomerate, sandstone, siltstone, shale. And then the other two, the dolomite and the limestone, are usually oceanic sort of deposits. And so those things would be like the limestone here would have been in oceans that once covered this landscape back 350 million years ago. And so that's part of the Madison limestone there. There are dolomites mostly in Missouri for the most part. And then you can also get kind of replacement rocks like chert, or you can get gypsum. Gypsum is a rock that's made out of the mineral gypsum, and so some people regard it as rock gypsum, but generally we just call it gypsum. So anyway, that is what it looks like to be in an orogenic belt that once upon a time used to be a platform succession here. Here's some more rocks that are slightly deformed here. You don't see nearly the level of deformation that you saw in Sheep Rock Canyon there, but Sheep Creek Canyon there. But here you can actually see that this is along the Green River, which is aptly named. You can see here that's the river down here at the bottom. But those are some rocks that have been twisted and slightly uplifted there. down below, but they're mostly flat-lying if you look into the distance here. And so those are all rocks then in the Flaming Gorge area, so that's pretty close to where Sheep Creek Canyon is there as well. So this is an area that has been slightly deformed, but it's not nearly as deformed as some of the rocks you saw in the last slide there. So as we move on to the next slide, I just wanted to show you a diagram. This is one of the things that geologists kind of do. They say a picture is worth 1,000 words, and geologists draw a lot of pictures. We do it diagrammatically sometimes, and so this is actually an image that was done by Carl Karlstrom, who's at Arizona State, I think. And so anyway, Carl Karlstrom works in the Grand Canyon a lot as a geologist. And he worked with some other folks here, and this was an image that was posted into Wikipedia, but I've kind of redrafted it myself just to throw some color on it here. Now, I tried to do this like discreetly. You always credit the people who originally come up with the work, and you can see his name on here, obviously, and where it was grabbed from was the Wikipedia here. But I used this actually in another place where I showed that these things actually have different colors in it. So the original was actually done in black and white. So I've added the color here. There are standard colors that we use in geology that may or may not correspond to the things you see in this course, because there's a lot of different colors that you get used in your textbook and other places. But here you can see the sandstones are all yellow. And so yellow is very commonly the color that we use to portray sandstone. Blue on here is the rock that tends to be limestone. And so if you see the kind of royal blue on here, or the darker blue on here, that's a limestone. And then the rock that may be just kind of sandwiched in between there, you can kind of see the light blue on there. That's a dolomite. So dolomite and limestone are almost identical, except dolomite has a little bit more magnesium in it. And the shales on here tend to be like have the dash pattern in them. So you can see here also that there are patterns that we use for various rock types as well. The brick pattern we tend to use for limestone. The brick pattern that has a little bit of a slant to it, that's one that we use for dolomite. You can see how like the little lines that divide the beds in there are slanted a little bit. And then for shales very commonly we use the same color as the color of the shale. So on here, the dashed lines, the ones that are dash, 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 and then you get layers of dashes over the top of that, those are all shales on here. And so you can see the Bright Angel Shale was one of the lowest of the Cambrian age rocks that's on here. And that's a gray shale up here in the on the right-hand side. You can see it labeled over there as Bright Angel Shale. There's also some red shale shown on here as well. And those are down in the Precambrian sedimentary rocks that overlie some of the more crystalline rocks in the center of the Grand Canyon here. And so the Grand Canyon's famous for two rocks down in what they call the inner gorge. In the inner gorge, you're very commonly going to see the Vishnu schist, which you can see labeled right next to the Colorado River in this diagram over here on the left-hand side. And then right next to that, you can see where the Zoroaster granite has intruded into that Vishnu schist. And so it's got a very irregular contact with the Vishnu schist there. So schists tend to have experienced a lot of pressure and heat, and the granite itself has a little bit less, so it doesn't show the deformation so much. But then there's older schists that are shown on here as well, so there are older intruses on here as well. So over here on the left, you can see a Horn Creek Pluton over here. There's a Brahma schist down here. And then there's also the Rama schist, and then there's an older sort of Elf's Chasm Pluton that's at the very bottom down here, which had intruded into the Rama schist down here. And so there's other igneous rocks on here, like the pegmatite over here. We'll talk about pegmatites when we talk about granites in here in a little bit more detail. And then, so in fact, there's several different kinds of unconformity that are illustrated here. Among those are where you truncate that Vishnu schist and overlay it with Precambrian sedimentary rocks. Those are going to be that's going to be a nonconformity, just like you saw with the flathead sandstone there. And then you're also going to see this entire succession down here below the great unconformity, what's listed as the great unconformity on the right-hand side over here, kind of at the bottom of the column on the right-hand side here. That great unconformity separates the Precambrian from things that are above the Precambrian, so Cambrian and younger age rocks or above that surface right there. And then you can see faults portrayed on here as bold black lines that cut through the successions. Basalt is shown in black, is the same color as the rock color there. But the unconformities, in fact, are these wavy lines. And so the wavy lines that you see in this diagram are all unconformities. So the one down here at the bottom is going to be a nonconformity. The one right here where it cuts out everything that's in the Precambrian, regardless if it's a crystalline basement rock or if it's sedimentary rock, all of those rocks are dipping at an angle away from that unconformity. And so that's regarded as an angular unconformity. And so the great unconformity is, in many places anyway, a angular unconformity. I list the types of unconformities up here at the top. They're in alphabetical order, so don't, it's not like I've tried to list these in any particular fashion here. But on here you can see that the great unconformity is an angular unconformity in the Great Basin, in the Grand Canyon area. It's very close to the Great Basin, that's why I was saying that, but it's not quite the Great Basin yet. This is still actually on the Colorado Plateau. So this is the great unconformity and angular unconformity. You also see disconformities on here. There's one that's up here in between the Redwall limestone, which is that second blue limestone on here. I've got it marked as a disconformity in some places anyway. I guess I haven't marked it on this diagram, but it should be a disconformity right there. And then so you've seen the nonconformities, an angular unconformity, and a disconformity just in this one diagram here. And we'll get into these in a little bit more detail when we talk more about sedimentary rocks. So those are all types of rocks that were deposited, pretty much flat-lying rocks, right? And so those would be regarded as platform rocks, in fact. So above the Precambrian basement rocks in there. And so, okay, so the next diagram on here, I can show you what these surfaces kind of look like in closer inspection here. That is actually the Bonterre dolomite over here on the left-hand side, overlying a clast of Precambrian granite, or Precambrian volcanic ash, actually, volcanic rock. It's like a rhyolite. So in that rhyolite clast, and then the rhyolite down below it are overlain by, in this case, dolomite. So dolomite over the top. It's kind of a sandy dolomite here, in fact. So some of the sand that weathers out of the granites, things like that, get incorporated into the dolomite there. Kind of a cool rock, and it's one of the most unusual outcrops we have in Missouri, because there's a nonconformity right next to this that is a nonconformity right about where my the lanyard is from my hand lens there. So geologists always carry hand lenses in the field with them, just so that we can look at the rocks up close and see the crystals and things like that, and be able to tell what they're made out of that way. And so I can tell you for sure that thing is a rhyolite that's kind of weathering yellow there, but the rock that's gray above it there is actually a dolomite. Well, you kind of saw the same sort of thing when we looked at that Tom Sauk Reservoir cut, right, where they were generating electricity just below the Tom Sauk pump storage unit. Over here on the right-hand side, those are all sandstones, in fact. In fact, it's a very pebbly sandstone there. This is from a recent trip from the Association of Missouri Geologists here, and people are looking at it very closely to try to find if they can see what the composition there is. And so this is a recent cut in one of the places that we visit, close to Stout Creek Shut-ins, actually, near Lake Killarney there. But that's the Lamont sandstone, which happens to be the basal Cambrian unit in Missouri. In many places, it's the basal Cambrian unit anyway. So that's Lamont sandstone over here on the upper right. And then down below, that panorama view right there is really one of the most beautiful places in all of Missouri, in my opinion, right there. It shows two rivers coming together right there, which is known as a confluence, by the way. A confluence is where two rivers come together. And in this case, the one on the left-hand side there, that's the Sauk River. Now, the river is actually flowing off to the north here, which is that arm that reaches away just above that tree in the foreground here. And so that is the Osage arm of Truman Reservoir right there. And then coming in from the west in the direction of the sunset there with the nice sunset reflection on it, that's the Osage River. And so the Osage arm of of Truman Reservoir extends that way. The Sauk River arm heads back down towards Lake Stockton. Actually, if you were to go to the left, you would eventually wind up at Lake Stockton if you went upstream there. So that is a place where the Burlington limestone crops out in cliffy exposures. You get like 2 miles or 3 miles of cliffs along there that are about 120 feet high along there. The only people who tend to see this, in fact, are either fishermen or duck hunters. And I've been down there a few times myself. In fact, I bought a boat just to go explore this area. It's really pretty spectacular geologically as well. I can explain that later at some point, and probably will, just because it's one of my research areas, and it's so fun to come to this area. That's the Burlington limestone there. That's close to Osceola, Missouri. So if you drive in between Springfield, Missouri and Kansas City, you're going to drive right near this area. This is just off of Highway 82. And in those bottomlands that you see out here cut by those rivers, those are the floodplains of those two rivers. It's really some of the wildest land you'll see in that part of Missouri. It's really beautiful through this area. So that is the Burlington limestone, which happens to be Mississippian, same age as the Redwall limestone in the Grand Canyon, and then the same age as the Madison limestone that you saw in Sheep Creek Canyon as well. Here it is, just outside of Springfield. Here, that's Warren Maservi, who's working with me on his master's degree right now. He's working on his master's thesis work right now. He's doing field work down in Glade Top Trail down in southern Missouri here. Anyway, he was my teaching assistant for stratigraphy. I teach stratigraphy as well, and we were looking at rocks all around the Springfield Plateau here, and those are some of the rocks that you see in the Burlington limestone here. You can see there kind of like there are little chunks in it. Well, those are actually crinoid columnals there. Crinoids are not extinct. They're actually still living in the oceans today, but they live in relatively deep water. But back during Mississippian time, in fact, they were one of the most abundant animals that lived. They call them sea lilies, which is kind of a misnomer. They are animals. They're not actually in the plant the plant domain there, but in fact, they are animals. And when they die, they kind of become disarticulated. You may see them if you're in the Springfield area. You've probably seen crinoids before. So crinoid columnals tend to be round. They look like beads almost. So if you're familiar with those sort of necklaces you got when you were a kid, you could stretch them out over your neck, and they were all bound together by a little elastic band or whatever. And then you could nibble off the candies that were actually kind of cylindrical in shape. That's what these things look like. Okay, and I don't know what the name of those candies are, but these are pretty cool. As well. Don't nibble on them, though, I would recommend. You can actually see the Burlington over here on the right-hand side where it's exposed just south of, in the southern part of Springfield there. And so oftentimes when people make new road cuts in an area, the geologists want to be the first ones there so we can see the freshest rocks and see the newest rocks that are there. If that's a road cut on the left-hand side in the upper right, that's also a road cut there. They drill into it, they blast it, and then what they do is they take that rock and then they put it in the slopes that may be on other sides of the hill. And so they do something in engineering, you would call it cut and fill, if you're making roads and things like that. And what it does, it kind of levels the road out so you don't have to go up a steep hill, or you don't have to go down a very steep incline, when you're going downhill. And then over here on the bottom, that is a piece of it's a photograph of the Potosi Formation, and this is actually at Echo Bluff. It's a state park, one of the newer state parks here in Missouri, and so this is really close to the areas that are around Round Spring, and then also close to the Current River area. We got to visit that back in August of this year. Really kind of a spectacular sort of place. So those are just some examples of some rocks that you see in a platform setting. You've seen the Bonne Terre Dolomite, you've seen the Lamont Sandstone, you've seen the Burlington Keokuk Limestone, and now you've also seen the Potosi Formation, which happens to be a dolomite. And so it's a dolomite. I want to show you a little bit here. This is kind of cool. This is a kind of a 3D rendering of what it looks like to be in the Springfield area. So Missouri State University, where I'm teaching and who this course is designed for, that's in the Springfield area. It's just under where I've labeled it Springfield here. But you notice in that whole area that's up in in the north sort of like side of this diagram here, this 3D diagram. It's a digital elevation model, and so the streams and things like that, the hills and hollows, in fact, tend to be kind of rugged and look like it looks a little bit wrinkled, I guess is what I would say. Well, those are areas that are below the Mississippian limestones that cover the bedrock that happens to be in the area around Springfield here. And so that whole surface is relatively flat there, and so that is a plateau. And in fact, if you look down here in the lower left down here, you can see a digital elevation model for, Missouri. And so you can see that the highest ground in Missouri is actually in the southern part of the state, closer to Arkansas there. In fact, Arkansas even has higher mountains than what Missouri has in the Boston Mountains. And so you can see there that sort of like, wrinkled sort of form. You can see where the St. Francis Mountains over on the southeastern part of Missouri there, where it's really rugged. And then areas in the Springfield Plateau tend to be over here on the left-hand side of that Missouri map down here. And so that is the Springfield Plateau here. And ironically, one of the highest points in Missouri, the highest point is called Tomsock Mountain, and that's in the St. Francis Mountains. One of the next highest places that you get in Missouri is just off the edge of the Springfield Plateau, and I think it's called Lead Hill, and it's very close to a place called Cedar Gap. So in between Springfield, Missouri, and the town that's closest to the edge of that Springfield Plateau, which is Cedar Gap, there's about 400 feet of elevation change, and so you actually go up 400 feet between Springfield and places just beyond Seymour if you head east on Highway 60. So Highway 60 cuts down. Eventually, you're going to go down a big hill, and you'll be down on what they call the Salem Plateau there. So those are really the four parts, or the four parts that are, some of them plateaus, as we regard as plateaus. The Springfield Plateau tends to be, the bedrock there tends to be these Mississippian limestones are relatively flat. And then the Salem Plateau, you get mostly dolomite. And then you also get some sandstone as well. And so the sandstone there is in the Rubidoux Formation. So Rubidoux Formation crops out around Waynesville and places like that, up around Rowlett also. So anyway, that is what you get in the Ozarks. And so this whole area was uplifted many, many hundreds of millions of years ago. And since then, it's been slowly eroding away. Limestones have a tendency to melt like sugar in the rain, whereas dolomites tend to be a little bit more resistant to that sort of weathering, especially if there's sandstones around it, and the sandstones can kind of buffer the erosion that's going on. Anyway, that's two parts of the Ozarks Plateau, and that's the name of our entire region here. So the Ozarks Plateau consists of St. Francis Mountains, the Salem Plateau, the Springfield Plateau, and when you get into Arkansas, and it's just at the very bottom of the diagram that you see over here on the left-hand side. In that map there, you can see the ruggedness of the Boston Mountains down there, and they can be up to like 2,500 feet high, so like 800 feet higher than what the Springfield Plateau is. Really kind of a neat area to live. So these things collectively are called plateaus or plateaus with an X. And so they've been uplifted vertically, but they haven't been deformed much. And so this is all platform area. So this, if we have the shield that's up to the north in the Canadian Shield area, here you get the plateau, and that's covered with sedimentary rocks of various ages here. And so that is the Springfield Plateau there. We're going to go on to mountains next. And so if we've talked about platforms, we're going to talk about the mountains next, areas that have been deformed. And so orogenesis, these are called orogenic belts. And so orogenesis is the Latin version for what it means to have mountain building processes operating. And so the actual events themselves are called orogenies. And so that's a mountain building event. So an orogeny happens when you actually have collisions between island arcs and continents, or two continents coming together, and you form mountains that way, or the orogenic belts. They tend to be long and linear, a lot like the Appalachian Mountains, right? So the Appalachian Mountains are considered a orogenic belt because of that. The Rocky Mountains are an orogenic belt as well. And so they tend to be lengthy in their distance, so it's an origin itself is actually all of the rocks that were affected in that mountain building event. So three different words that begin with orogen here: orogenesis, orogeny, and origin. So, but they all have very similar connotations regarding mountain building processes. But not all mountains are the same. Some are orogenic belts, but we can also have volcanoes, and we can have fault-bounded mountains where all of a sudden you have uplift on one side of the fault and maybe downdrop on the other side. And so that leads to things that we call extension, like you can open something up like it's an accordion, or you can put it together, right? So you can shorten it that way. And so you can extend it or shorten it as well. There's a lot of other kinds of mountains out there. There's some domes and things like that, but these are the main ones that we want to talk about first anyway here. I've got some others to show you at the very end down here. These are photographs from Wales right here. So this is absolutely stunningly beautiful. That area right there is called Snowdonia, and it's a national park in Wales. Now, Wales is on the west side of Great Britain. Great Britain's that big island that England and Scotland are on. Well, Wales is the country that's off to the west. They have their own language, they have their own customs, and there are Celtic peoples that have been there since the beginning of time, practically. So the Celts came into this country probably at least 9,000 years ago, something like that. Snowdonia here is some of the most rugged mountains in all of Wales, and so those things get up about 3,000 or 4,000 feet right there, so higher than anything in Missouri. So Snowdon is the highest of the peaks there that you can see in this image. Now that's from Wikipedia here, but that's one of my photos down here on the lower part here. If there's mountains in the north of Wales, there are also mountains in the south of Wales, and so the mountains in the south of Wales include the Black Mountain and Brecon Beacons. And so this is from Brecon Beacons right here. And that nice flat top mountain that you see in the foreground here, that's called Penny Van. And so Penny Van is it was glaciated at one time on top. And so you can see that it's flat beveled at the top up there. But the top of that's about 2,200 feet, I think, something like that. Really quite a spectacular view from up the top there. That's one of my friends actually here. That's Garrett Owen right here in the lower left in that photograph. He was kind enough to, he and his wife Wendy were kind enough to take me on a hiking trip here to Penny Van. So those are all places that are mountains, right? So if Missouri has limited mountains, we're mostly a platform sort of setting. There are mountains in Arkansas, the Boston Mountains, which are relatively flat as well. They're not really highly deformed. But when you get into the southern part of Arkansas, you can get into the Ouachita Mountains there. And the Ouachita Mountains are really quite deformed. And it is an orogenic belt when you get into the Ouachitas. That's Ouachita actually with an O. O-U is how it's pronounced, Ouachita. So those are some mountains here from Wales. I got to show you some, mountains are one of the things that draws humanity to them. It's like mountains they have a majesty, right? And so they are things that inspire the imagination. They inspire people to do better, I think, in some ways. And so this is Mount Everest right here, the highest mountain on Earth. And people die climbing it every year, practically. But anyway, it's one of the great feats that you can do here. I think it's Lhotse is the smaller mountain that's just, well, if you went directly below the O in orogenic belts there, you would land right on top of Lhotse there. So Lhotse is that mountain. Mount Everest is the one in the middle there, of course. And that's the base camp is going to be down there in that valley that's just below Everest there. And so people, when they climb this, they actually go off to the right there and up that valley. And there's a glacier that's in that area. And so you have to cross that glacier and then climb up between Everest and Lhotse in a series of switchbacks. And it's the endless climb for there almost. It's 17,000 feet at the very bottom where base camp is there. But the top of Everest there is over 29,000 feet, so another 12,000 feet that you have to go up to get up Everest there, and it's a very difficult climb. Let me put it that way. So most mountaineers have that as a goal in mind. I never had that as a goal in mind. I love doing alpine mountaineering, but not when it requires that much effort. I guess I don't know. It's just it's something that you have to be kind of born with, that sort of thing, to want to be able to climb high mountains like this. And they can be quite challenging, I have to say, as well. Here's the location for where that is. So it's in the Himalaya. And so the Himalayas, they're in between Nepal and China, well, the Tibetan Plateau part of China there, and in Bhutan as well. So the Himalaya are all those mountains that are snow-capped in this map right here. There's a few things I have to point out on this. I wanted to point out a whole bunch of the mountain ranges on here, and many of them are really, really high. So you can see the Hindu Kush over here are in Afghanistan. The Karakoram includes the second highest mountain, or the second most difficult mountain. I think it's actually technically more difficult to climb than Everest, would be K2, they call it. So K2 is in the Karakoram there. I'm going to show you some pictures of these things as well. And then the Tian Shan is on the north side of the Tarim Basin there. And so these are all areas, that's in Kyrgyzstan and really close to Kazakhstan there as well. So China and all those areas in western China are just notoriously rugged. The whole landscape there is very rugged. And you probably wonder, is like, well, that's another one of these plateaus too, right? So the Tibetan Plateau, that's interesting, right? It's right next to the Himalaya. What happened there? Well, I kind of hinted at this when we talked about plate tectonics. I said India, remember when Gondwana broke apart and India went careening across the ocean and slammed into Asia in slow motion anyway. When it slammed into Asia, it caused the Himalaya to rise up, and then you would actually take some of the subducted parts of the Indian continent and then have that underplate underneath of the Tibetan Plateau. Now, some people think that it's also detached in some places, so the part that was underplating it is actually dripping from the bottom of the Tibetan Plateau, and actually mantle material, which is lighter in density, buoys up that area then. And so you take that dense crust is going to sink, and then the light material in the mantle will raise it up. And so that's the Tibetan Plateau right there, the underplating and uplift from the delamination of that subducted plate that used to be part of the Indian plate there. Now, you can see mountains go across this entire landscape, can't you? So you can see them all the way from Laos over here in Southeast Asia, extending through southern China into the Tibetan Plateau. It goes on into Kyrgyzstan and Tajikistan and on into Afghanistan here. And then it goes on into Iran. And so Iran is very mountainous as well. And some of those mountains, in fact, in the north of Iran there are just north of Tehran there. That's the Elbrus Mountains through there. It's a place I'd love to visit sometime, but not right now. Thank you very much. So this is the area, in fact, that is very rugged. It goes all the way into across Europe, in fact, and so it goes into what they have is the Alps over there, and so both the Carpathian Alps and then the Dolomites, and then you can get into the Swiss Alps, and then you finally get to the foothills of the Alps in France and places like that. Really spectacular, and stretching across the entire continent here. You know, when India slammed into the southern part of Asia here, and it slammed into it, you can kind of see how some of the bands are distributed out there. That's known as escape tectonics. So when you step on a tube of toothpaste, it squirts out somewhere. That's what happened to part of the Tibetan Plateau there. It just kind of like squeezed out to the side there from that collision with the Indian subcontinent. India comes in, slams into it, and that material squirts out to the right there, or to the east there slightly. And so that is what they call escape tectonics. So that is part of the story here. Let me show you some more pictures now. So this is Nanga Parbat, and this is in the Karakoram. Now, this is really a beautiful photograph, and I wish I could take credit for it, but it's not mine. I've never been to this part of the world. But Nanga Parbat here is a spectacular, beautiful mountain. It is one of the places where you get the largest expanse of nothing but mountain face there. And so that is that face right there that you can see in this image. Nanga Parbat, as it turns out, if you look it up in Wikipedia, you'll find that it has the highest uplift rate right now. So it's actually going up still, and it's going up at a rate of about 7 millimeters per year. Now, it doesn't sound like much, right? But give it 10 years, right? So that's a little bit, that's about half a foot, okay, in 10 years. And then it's going up still. So plate tectonics never sleeps. It keeps going on. It gives us mountains and things like that. And so it's a very slow process. If the plates are moving about as fast as your fingernails are growing, so are the uplifts on some of these mountains as well. Here's a photograph of Tian Shan, and so this is from in that area that is in northwestern China, and then Kazakhstan, Kyrgyzstan, Tajikistan, and even Uzbekistan here. So those are all places that are really remote on Earth. There are people who live there, obviously, but these are very seldom visited by most Westerners anyway. And so it's the Tian Shan, just spectacular mountains here. On the next slide here, this is part of the Karakoram now. And so I'm just kind of giving you a grand tour here. And so these are places that the climbers can get to. This is in Pakistan right here. And so Pakistan, they love to have climbers visit Pakistan, generally. And as long as they don't get too many of them, I think. And so some of the mountains here, in fact, include Gasherbrum, one, and there's like 4 of the Gasherbrum peaks. And so that's the map that shows their location down here. There's 4 that are very common. You can go all the way up to 8, I think, all together in these things. But different pieces of the same mountain there. And so that is some of these high peaks, and you can actually see a mountain climbing bunch that's just down below Gasherbrum 2 and Gasherbrum number 3, which is the high point in the background there. Maybe 3, maybe on the left-hand side. And no, I think 2's on the left-hand side, 3's in the middle foreground there, in the middle image on the right-hand side. So that's in the Karakoram, some of the most rugged mountains on Earth. And if you look from this like aerial view right here that's over on the left-hand side, it's like, oh my gosh, there's no roads in here, or very few roads. And so the roads that you eventually have to get in with pack trains and things like that. So they have mules and things like that would bring your climbing gear in, and then you would hire locals to actually, guide the tour for you. But K2 is among the mountains there. Next, I'm going to take you to North America. North America has this same sort of story in places like where you get the Alaska Range. And so this is the Alaska Range looking from the north towards the south here. In this image, it looks a little bit like an old postcard, like they used to tint these things. And in fact, that's from the national map. And you can do this yourself. In fact, you can look at 2D and then 3D imagery of digital elevation models in that application. It's a web-based application. So that's direct. That was from a screen capture from the U.S. national map there. And so the USGS publishes that, in fact. That mountain that's over on the left in the middle there, that is McKinley. And so it's only recently had its name changed back from Denali. And so, but it's still part of Denali National Park, okay, just to give you an idea here. So that is Denali National Park in Alaska. And over here on the right-hand side, I'm pretty sure that's Silver Throne over there, which is one of the higher peaks in the Alaska Range as well. Now, this is a spectacular mountain range, and that is 20,000 feet high right there. It is a huge mountain. It's the largest in the North American continent. In the contiguous United States, we have a peak that's in California that's known as Mount Whitney. I've actually partly climbed Mount Whitney. We had to turn around when one of my climbing partners had some issues with altitude sickness, and so best not to risk one's life when one climbs and does alpine mountaineering. We were post-holing in the combe that's just down below Mount Whitney and had to turn around and come back. Never tried McKinley here and don't know that I ever would. But in fact, I have known people who have climbed it. I know people who have lost their lives, who lost his life on it. And so, in fact, I want to show you his image here. I want to show you a picture of McKinley from looking from the north towards the south here, and you can see its reflection in the lake on the right-hand side. And that's Muggs Stump over here on the left-hand side. His name is Terrence, but he went by Muggs. I knew him and his brother, Ed Stump, and they were in Antarctica when I was there. And so Ed and Muggs And Paul Fitzgerald and a few other folks were on an expedition to look at the Vinson Massif. It's one of the higher spots in the Antarctic continent. I think it's 17,000 feet or so there. And this is that's what he did for his passion. Oh, he used to be, I think, a football player for Ohio State University back in the 70s or 80s. And but he used to always accompany his brother on these sort of expeditions. And what they would do, they would collect rocks from the very tops of the mountains and be able to get uplift rates based on their collection of rock samples. They would do something called appetite fission track dating. And so appetite fission track dating gives you a measure of how rapidly mountains are rising. And so that's what they were doing on Vinson Massif. Mugg lost his life just the year after that when he was guiding some other climbers on McKinley as they were climbing it. Now, Muggs was he's an international phenomenon. He was one of the most fascinating alpine mountaineers that I know of. And I want to credit, this is a photograph. I couldn't find any images of Mugg Stump. I don't have any of myself of Mugg, so I grabbed this from Michael Kennedy, who also wrote for Patagonia and Climbing magazine here. So, that's it shows you his sort of attitude. He was a very devil may care sort of person here, but he was an expert climber and he was not careless. And sometimes you get into situations in alpine mountaineering, you never know what's below you. And according to Wikipedia, anyway, he lost his life by falling into a crevasse on McKinley there. Spectacular person. And so his brother is too. Ed Stump was in the Antarctic one year that I was there as well. Ed lost one of his big toes to frostbite that year. So it just goes to show you that you need to have the right gear on for this, and if Muggs is an international climber, the one that lost his toe wasn't using the insulation socks that other people would wear. Essentially, they're like putting your feet in plastic bags, but what it does, it keeps the moisture in your feet, so your feet tend to get really wet, which is not necessarily a good thing if you're in alpine conditions. Anyway, so the next slide here is another set of mountains here, and those are the Appalachian Mountains. And that is a geologic cross-section, in fact. So east is off to the right there, and that's the coastal plain. You can see where the Blue Ridge Mountains are on here. And then you can also see off to the left over here, where you get closer and closer into what is known as the Cumberland Plateau, and that's sort of setting over there on beyond the Valley and Ridge province there in the middle. So the Appalachians are in the east coast, right? And so those are the high mountains there. They get up to about 6,000 feet high. And you can tell from here, even on this diagram, you can see that it's very mountainous, right? And so you can see some shots down here at the bottom that shows the rugged nature of the Appalachians. Very isolated sort of place. And in fact, in the early history of the United States, that was kind of the limit about how far you would go into the interior until people kind of opened it up in the late 1700s, and the first settlers came into the Midwest then. And so that was Daniel Boone and other folks who crossed over the Cumberland Gap, in fact, and so the Cumberland Gap brought them into the Cumberland Plateau, and they would establish places to live and work and trap and do all sorts of things. The Ohio River runs on that side as well, so it was easy for the early settlers to encroach upon the Native American lands that were, it was designated for Native American lands up until most of those treaties were broken. In fact, this was the history of North America and the westward expansion of colonies that went into the rest of North America. And so anyway, that is the Appalachians right there. In the Appalachians, in the diagram at the top, you actually get a sense for how these are a whole series of thrust faults, and you can actually see the rocks are stacked up and pushed together like a deck of cards, right? And so the deck of cards is getting other cards pushed over the top, essentially there. And that's the way people think that these thrust faults work. In the next image here, you can actually see a digital elevation model of the Appalachians here. And two things to show you here, actually. You can kind of see that you can, first of all, see that it's a belt there. And then it stretches all the way from Maine, in fact. It switches up and to the northeast and beyond this map here. And it stretches all the way into Alabama in the south here, close to Birmingham, in fact. And so that's the Appalachian Mountains, but you can trace those down from northeast to southwest here. And then what they do is they dive underneath of the Mississippi River and pop out again like a porpoise on the other side in Arkansas right there. And so that's an extension of the Appalachians known as the Ouachita Mountains in Arkansas. So you can kind of see the outline. I hope you know what the outline of Arkansas is on here. I'm not sure that all of you would know that, but maybe you would at least recognize Missouri. So the state just south of Missouri there is Arkansas. And you can see the high Boston Mountains in there, which are higher than anything in the Ouachitas, but in fact, they can get up to, well, actually the highest mountains are in between the Boston Mountains and the Ouachitas. That would include mountains like Mount Magazine, I guess, is actually the highest mountain in Arkansas, 2,800 feet high, I think, something like that. The highest that are in the Bostons, I think, is about 24, maybe 2,200 feet high. In the Ouachitas, it's not quite that high, but some of them are pretty high there as well, like around Queen Wilhelmina, and then also there's some other mountains in there that are pretty high. Anyway, it's an extension of the mountain belt that is the Appalachians, and so they went up in a time period called the Pennsylvanian, and you can get a sense of what it looks like down here. That's actually the Appalachians, that photograph that you see, the Ouachitas that you see in that photograph where the trees are changing color and so forth. So that's in the Ouachita Mountains down there. So these mountains formed, the Appalachians formed when the ancient continent of North America, which was known as Laurentia at that time, collided with Pangaea, the African part of Pangaea, in fact, and so those mountains went up as a result of that collision. So that was the orogenic belt, and so it's called the Appalachian orogeny. And so in the Ouachitas, it's called the Ouachita orogeny. In the Boston Mountains, we don't call that an orogeny because they're flat-lying rocks and they aren't that deformed. The whole thing actually went up very, very slowly, and so that's part of the Ozarks Plateau, and so all of that area, in fact, was what they call epirogenic uplift, or just vertical uplift, essentially, but probably a result of that collision as well. And so that was about 300 million years ago when that collision occurred. So some of the other mountains that we have are not orogenic belts, but I can't say that actually, because the Cascades are a mountain belt, but they're discrete volcanoes that are in that are regarded as the Cascades. And so the entire belt would be the Cascade Mountain Range. But in fact, there are individual and isolated volcanoes all along there. It starts down in Mount Lassen in California, and then it runs through places like Mount Mazama or Crater Lake. You may know it as that. Mount Adams, Mount McPherson, I think it is. I'm not sure exactly what it is. Mount Rainier over here on the right-hand side. Mount St. Helens is in Washington State. Mount Hood is in close to Oregon. And then Mount Rainier is just above Seattle and Tacoma in that area. And Mount Rainier is like 14,000 feet high. This is Mount Shasta here. And I have climbed Mount Shasta, actually. That was really I think it's the highest mountain I've actually climbed. It's 14,000 feet high. I didn't list it on here, but it's over 14,000 feet high. And I climbed that with my friend John Kramer and a few other folks. And so I'm going to show you some pictures actually from that climb, which was really a fascinating climb. Did that in 1999. Now this is an aerial photograph here. This is up above what you would normally have as a drone image here, right? So a photograph taken and posted to Wikipedia here. You see that sort of gulch that runs right through the middle of that diagram there. There's actually a road that you can kind of trace on here that goes to a place where you can go. And what you want to do is to camp there, and then you climb the thing. As it turns out, this is the same friend who had issues on Mount Whitney with some, altitude sickness. And in fact, so we didn't nearly spend enough time on the mountain before we climbed it. I was actually living at a little bit higher elevation than what most of these guys were. And so when we climb this thing, we use we use what they call crampons. You can strap them onto your boots, and so you have pretty much rigid boots that you're wearing, and usually they're going to be, like I have got a set of Koflak boots that I use for my platform, and then I use what they call foot fangs for my, I don't even know if they make them anymore, but foot fangs have kind of a platform sort of setting for the crampons that you strap on. Essentially, they bind onto your feet, essentially. And then you also have gaiters that wrap around your pants and everything, and so you have bibs on and so forth, and then you layer up, right? So you don't want to get overheated, but at the same time, you don't want to get frostbite. And so we climbed up what is known as the avalanche route there, and so the avalanche route going up, we went up from about 8,000 feet to the top of this, over 14,000 feet, 6,000 feet up and 6,000 feet down in the same day. So in the next image here, you can actually see that same USGS from the national map. It's the U.S. national map here. This is the image from where we were climbing, essentially, what it would have looked like. And so we went up that sort of gully that goes up to the top of the mountain here. So that is an area that is really pretty spectacular. And people, most people, oh, you went up that thing? It's like, well, so I was a little bit younger, okay? It was 25 years ago, but 26 years ago, 27 years ago now, 26 and a half. But, people still die on these mountains. And when I was living in California, there was a guy who wandered off the beaten track and they never found his body. And so, you can mount search and rescue, but if you fall into a crevasse, it's like, well, good luck trying to find your body then, especially when you don't know where the tracks are, if the wind picks up and things like that. There's a lot of things that can, hide your tracks. Even during the day, your tracks will melt and things like that if you're exposed to the sun and everything. So the day that we climbed up this thing, that's where everybody was heading up that day. There was probably about 40 people that went up the mountain that day. You can see our camp down here at the bottom down here. So we had camped probably around 8,500 feet, 8,600 feet, something like that, in a little campsite there. It was me and Ray Yuritsa. He was a mountaineer. He was originally from Armenia. And so Ray was a computer programmer in L.A., and Ray lost his life in an alpine mountaineering accident. Well, it wasn't an accident. It was a medical emergency, and he lost his life where he was an experienced mountain climber. And he was survived by his wife and children. And John Kramer is a good friend of mine. And John Kramer and George Hecht, good friends of mine. Hal Halverson as well. These are all people I've known for many years, and so it was a real pleasure. And one of the great memories that I hold, in fact, is in alpine mountaineering. And so I guess what I'm not trying to harp on this, but I'm just trying to tell you is find out what you really like doing in life. If I were to give any sort of life lessons and sort of things like that I think are really kind of important, if you find out you love alpine mountaineering, and it can be a real psychological boost. You don't think about anything else other than your own survival and making it up along with your friends and looking out for them when you're on these climbs like this. And so it's very important to look out for one another. And so these mountains have a way of healing as well. So it was one of the most difficult times I've ever gone through, let me put it that way. And in 1999, I was coming out of a real deep funk, and it can really give you the mental and physical boost that you kind of need. And so remember I said that this course is not accurately named. It's not the instruction manual so much as it is Adventures in Geology. And so I wanted to share that with you. So, okay, one more slide here to show you of that climb. And so that's Hal down here coming up the, so many people have climbed it this day that leaves a little gully through there, which is kind of fun because every time that you climb up this thing, when you come down it, you get to glissade, which means that you hold your ice axe in one hand and use it as a brake. And so essentially you just slide down like you're on a toboggan all the way down. And it is so fun. That was the highlight. It wasn't getting to the top. The highlight was actually glissading down this mountain here. And so you can see, we would have camped, I think you can actually see some tents in the far distance down there. So that's about 8,500 feet there. So this is up towards the top of that avalanche gully there. And here we are putting on our crampons over here on the right-hand side. You can see some crampons on John's shoes there. We're probably taking them off right there. So this is on one of the bands. I think it's called the Red Band, or I think it's the Red Band here on Shasta. So, but anyway, we're taking off our crampons, getting a little bit of food to keep our energy levels up. And on the right hand side, that's me with my boots and gaiters and bibs, and then also, it was a warm day that day actually, so just pretty minimum sort of like gear on right there. It was cooler in the day, so we had coats and vests and things like that on from the earlier sort of parts of the day. But by the time we got up here in afternoon, like 1 or 2 in the afternoon, and then we glaciated our way down and we had to part company when we were at the bottom down there. It's one of my best memories of getting to share that with some good friends. Okay, so there's other types of mountains as well. These are some of the fault block mountains here. This is the Notch Peak over here. That's one of the places I dearly love on this planet as well. And so the Notch Peak is in the House Range in western Utah, kind of west central Utah, and the House Range and the Confusion Range, and then the next range over is going to be in Nevada beyond that, and that's going to be the Snake Range as you go west. So in the House Range, there are very many beautiful mountains there, but this is the highest in the House Range, and that's only about 9,600 feet, 9,660 or something like that. And that's called Notch Peak right up here. So Notch Peak actually is the entire peak here. And so there's like the North Notch and the South Notch and things like that. Well, that's the South Notch right there. Up at the top of the House Range here, there's actually bristlecone pines. It's some of the most dense wood you'll ever find on Earth, and it's illegal to actually collect it or to keep it. But bristlecone pine is really kind of a neat wood that grows up in the high elevations in these sort of mountains. And that's a mountain that's made out of limestone right there, which is pretty cool. But in the foreground in here, I'm going to show you some more images of this, but in the foreground down here, that's a granite. And the granite is much, much younger than the limestone here. And so when that granite intruded into this area, it baked many of these rocks, and actually, so they're very, very hard because of that intrusion. And it made them more resistant to erosion because they were baked hard. And so what you see then is, in fact, the result of that is these mountains just don't break down all that fast, even though it's a really steep canyon right there. As far as I know, I don't know if anybody's ever climbed that because there's just too many loose rock on it, I think, to go up that vertical face there. I know that people are capable of doing that, but I think if nobody hardly ever climbs it, that they're not going to go up something that nobody else has climbed like that. And so that's a good way to write your own epitaph there, if you go up something that nobody else has climbed. Just a few more mountain pictures here. That's the Front Range over here, and the Loveland Pass goes over the Front Range, essentially. It's close to a place called Georgetown in Colorado. When you get to Georgetown, you can take your pick, kind of. You're going to go over the pass, or do you want to go through the Eisenhower Tunnel on Highway 70? And so in this case, we decided to go over Loveland Pass here because it's just so spectacular. You can see the road that's winding its way up to Loveland Pass here. And I think Loveland Pass is about 11,000 feet high. And the middle picture here on the left-hand side, that's Mount Law. Mount Law is not all that high, but it's one that I have climbed, in fact. But it is, and it's not that steep or anything either. But it's just one of the areas that I dealt with in my dissertation studies in the Great Basin of western Utah and eastern Nevada. And then in the Snake Range, you actually that's Jeff Davis Peak over here. So that's really close to that mountain that I think I've already shown you, in fact, Wheeler Peak that we talked about earlier. And so, but that is one of the areas that's in the Snake Range. And it's also a part of the Great Basin National Park there. In the next photograph here, you can actually see another one of these images that I created from looking at the national map. And so you can actually see Notch Peak on there, and then you can see where the Notch Peak intrusive is here. So that's a granitic intrusion. Now, the reason I show you this is because that is a small intrusion. It's less than 100 square kilometers, and that puts it into a group that we call stocks. And so stocks are really kind of small, locally kind of important features, but they're not as big as, like the Sierra Nevada batholith. So batholith is much, much larger in scale than what a stock is. And so this is the Notch Peak stock right there. That's in the central part of the house range there. Mount Law is down in the southern part of that. So this is another mountain range, isn't it? So you can get mountain ranges even in places that are fault blocks like this. Yes, you can. And so Notch Peak went up, and the rocks that are at the bottom of this, in the bottom of that valley down there, are the same age as the rocks that are at the top of Notch Peak. And so there's about 5,000 feet of throw on that fault right there, which is pretty spectacular when you think about it. Now, this is not regarded as an orogeny. Now, this is a little bit of a conundrum for you, because you're going to think is like, well, aren't these mountain ranges all related to collisions and things like this? This one's not. It's actually related to something we call extension. We've pulled these mountains apart. Some of the blocks have gone up and some of the blocks have gone down. If you can imagine an accordion slowly sort of like expanding, you lay it down on a table or something like that, and the accordion just kind of like flows outward. That's kind of what these rocks did. And so Notch Peak, in fact, is just one of those areas that happen to have been in the upside. And then the valley down below it, it's called Antelope Valley right there. And Antelope Valley falls down about 5,000 feet or more. And so that's kind of cool. Here's more of a diagrammatic sort of view of that. And so you get what they call normal faults. And so we're going to get into normal faulting later on when we talk about geologic structures in this course. It's more common than you might think in the West. And so that's called a Horsten Graben right here. And you can think of graben as being like a pit, essentially. And so it's like a groove, if you will. And the horsts are actually the up parts. And so the horst is going up, and then the graben's going down like this. And so you're pulling it apart. That's called extension. So when you pull it apart like that, these things will actually keystone in. The valleys will go down, and the horst or the up parts will go up then. It's not the only place that's done this, and then so even the Tetons have experienced this sort of activity. So the Tetons, in fact, here are right next to what they call Jackson Hole. So Jackson Hole and the Tetons have experienced. So the Tetons went up and Jackson Hole went down. There's a map down here at the bottom. So this is before I tinted the whole thing, but Jenny Lake is over here. That's a glacial lake down here. Glaciers used to dump out of the mountains here. You can see the U-shaped valleys that cut through the Tetons here. That's Grand Teton over on the right-hand side here. It was named by some French trappers who were in this vicinity early on, and so it means large. Well, anyway, I won't explain what it means. You can probably figure it out on your own there. But the Tetons go up like that, and so this was an area that was populated by Native Americans, and then also by the earliest European sort of heritage folks that came into this area were usually traders, fur trappers, folks like that. And so this is Grand Tetons here, another one of these fault block sort of mountains right there. Now, the next one is a massif, and so massifs, in fact, are related to intrusions. And this is in the Sierra Nevada batholith, and if we talked about stocks being less than 100 kilometers square, batholiths are larger than that. And so the Sierra Nevada batholith is absolutely huge. It stretches all the way from, close to Death Valley, all the way up past Lake Tahoe. And so it stretches all along that Nevada-California border, but it's mostly in the California side there. In fact, I think it's all in the California side there. So that is one of the key mountains, in fact, in an area that's called the Yosemite Valley. And so Yosemite Valley, of course, is a national park, and that's Half Dome that you see over here. So Half Dome probably used to be a whole dome at one time, but half of it either slid off or was removed by the glacial activity that went through this valley back during the Pleistocene. So in the Pleistocene, this whole area was covered with ice, just like the northern continent was covered with ice. So was Yosemite Valley. So these are high mountains in here. So, if Mount Whitney is over 14,000 feet high as well. Anyway, this is Yosemite Valley through here, and that's a photograph of Half Dome there. I've been camping in this area in the wintertime, and I've seen people with their aid climbing. They actually have these sort of litters that they will haul up the mountain, and then they camp along the face of that bluff, and they do what they call aid climbing. They can set protection and then climb this thing. It's more of an arm workout than anything. but in fact you can climb things that are over vertical even if you have the right sort of gear. Never had an interest in that sort of thing. Give me a walk up any day. But Yosemite is one of these places that's a paradise for climbers. And people have free climbed many of the routes in this area. I don't think that they free climbed Half Dome, but they certainly have free climbed places like El Capitan, and there's a few other ones that are free climbed, obviously. So anyway, this is Yosemite Valley here. That you can see the image over here on the upper left. That's Half Dome's shadow that you can see in that image. And then the Yosemite River runs out of that valley. It's very interesting because the upper slopes of that valley are U-shaped from the glaciers. But as you get farther and farther down valley, it becomes more like V-shapes that are associated with the stream cutting in and eroding into the bedrock in this area. And so when you finally get out of the granite there, it gets more steep in the valley. And so anyway, in the area where this was taken, you'd actually get kind of a more U-shaped sort of valley here from the glaciers. So that's the Sierra Nevada batholith here. Yeah, you remember very first lectures that we talked about and how, you can be an artist and be a geologist. This is a painting by Albert Bierstadt right here. And he was always inspired by the grandeur of mountains. And so this would have been a sunrise in Yosemite here. And actually, that would have been sunset in Yosemite there because he's showing you El Capitan on the right-hand side over here. He doesn't show you the true aspect of Half Dome over on the left-hand side, but I assume that's probably what he was thinking it was. Anyway, that is some of the more spectacular mountains in North America right here. I've got just a few more to show you here, but not many. In fact, just one more, in fact. And so we're going to go to the very southern part of South America next here. And so this is called the Torres del Paine. And so the Torres del Paine here is like a volcanic, it's an intrusion into igneous rock, actually. So it's a diabase intrusion into granites, I think, here. And so that is part of the Torres del Paine massif right here. So massifs involve really thick granites and things like that. So massifs are another type of mountain, essentially. So anything that's granitic is going to be regarded typically as a massif of some sort, unless it's very small. Okay, but the larger ones are regarded as massifs. And so this is in Chile. And so in Chile, you get these sort of U-shaped valleys just like you do in the Sierra Nevadas. And you can see over here in the upper left, that's from Google Earth Pro there. And you can see some of the glacial outwash waters that come out of the glaciers that go into the lake. It actually gives it that sort of like startlingly beautiful greenish blue sort of tint. The greener it is, typically, the more silt is in it from the grinding of rocks and so forth up valley by the glaciers. So that's glacial debris, the silt that gets into the lakes that gives it that sort of lighter color. And then the blue is also still got the silt in it like that, but less so. And so Torres del Paine, you can see over here on the right-hand side. Those are just a couple of images I grabbed from Wikipedia there. And so these are actually on my bucket list. And so if my wife were listening right now, she would know that this is on my bucket list to go visit the Patagonia and to see the Torres del Paine. Anyway, that is mountains. We talked about mountains. We've talked about plateaus. We've talked about platform and shield in here as well. So the platform is the area covered by sedimentary rock or sediments. And then the shield itself is where all that's been stripped off. But both the shield and the platform together rest upon the craton. So the craton is the core of a continent, the strength of a continent. These outer sides out here, these other parts are typically where island arcs or other continents have collided, and you get these orogenic belts like this. And so orogenic belts can lead to mountains. And so you've seen a whole number of different kinds of mountains. You can get orogenic belts that are block faulted. You can get some that are intruded and give you massifs. And then you can also have places where there's subduction that give you volcanoes. And so in California, Oregon, Washington, and on into British Columbia, those are all like volcanic origin there. It's still an orogenic belt called the Cascades, but they're all focused around volcanoes there. That's it for now. So this is one of two lectures that I'm recording today just to get these things uploaded for you, just to give you a little bit of advance on what's going on here. And so we've got one more presentation on plate tectonics, which is kind of the keystone for understanding geology in general. So we will do one on convection next. And so thanks for your attention. And I guess I'm making this my byline for the whole thing. I'll see you on the flip side. Cheers now. Talk to you soon.